In this video, we'll begin to learn how to find antiderivatives of various functions. In order to evaluate definite integrals, we need to be able to find an antiderivative of our integrand. In this case, we might easily guess that an antiderivative of x cubed is 1/4 x to the fourth. Then we evaluate this between x equals 1 and x equals 2. We get 2 to the fourth over 4 minus 1 to the fourth over 4, which gives us 16 minus 1, 15/4 as our answer. It will be helpful as we proceed to have a notation for this antiderivative of our integrand. We have lots of notations for derivatives. Or we could write this as 1/4 x to the fourth prime, but we don't yet have a notation for an antiderivative. A reasonable choice might be this integral symbol without the endpoints of integration. We call this an indefinite integral because it doesn't have these defined endpoints of integration. But we want this to be every possible antiderivative, the whole family of possible antiderivatives, so we need to add an arbitrary constant onto our answer. This constant doesn't have to be c. It could be any other letter that we might use as a constant. The integral of secant squared theta d theta would be tangent of theta plus c. At the moment, we know a handful of basic derivative patterns from differential calculus, and we can simply undo those patterns in order to find a handful of basic antiderivatives. For example, we might know that the integral of cosine of t dt would be sine of t plus some constant, here I'll call it k, because the derivative of sine of t is cosine of t. We can always check our answer to any indefinite integral problem by merely differentiating our answer. Now, what if I wanted the antiderivative of cosine of 4x dx? I might guess that the answer would be sine of 4x plus some constant. But to check that, I could take the derivative of sine of 4x. This would be cosine of, leave the inside part alone, times the derivative of the inside part. I have 4 times cosine of 4x. That's not what I want. So I might think of adjusting my guess here. My guess is 4 times as big as it should be, so let me divide that by 4, multiply it by 1/4. Now when I check my answer, I get cosine of 4x, which is exactly what I want. Notice when we check the answer here, we use the chain rule. I could, for example, compute the derivative of sine of x cubed, and this would be cosine of x cubed times 3x squared. I just used the chain rule. So this tells me that the antiderivative of 3x squared times cosine of x cubed would be equal to sine of x cubed plus some constant. Another way to think of the chain rule is in terms of its Leibniz form. For example, if I have y equals sine of x cubed, I might express this as y equals sine of u, and then u equals x cubed. So when I put these two things together, I get y equals sine of x cubed. I know now that dy du is cosine of u, and du dx is 3x squared. So writing down the Leibniz form of the chain rule, dy dx should be dy du times du dx, which in our case would be cosine of u times 3x squared, but u was x cubed, so this becomes cosine of x cubed times 3x squared, and this gives us the same answer we had before. Now in practice, we don't typically use this Leibniz version of the chain rule to compute derivatives, but this idea might help us find certain antiderivatives. For example, if I wanted to find the antiderivative of 3x squared cosine of x cubed dx, I might think that this is the result of some chain rule differentiation, but I might not know exactly what that could be. Notice in our previous work, we substituted u for this inside part of the cosine function. Let's do that here. I'm going to let this inside part of the cosine function be u. I'm going to write u equals x cubed. That tells me that du dx will be 3x squared. You may remember differential notation. We could rewrite this derivative statement as du equal 3x squared dx. Back in differential calculus, this was just some notation that we occasionally found useful, but here with indefinite integrals, we'll find it very useful. Notice that 3x squared dx I have right here appears in my integral in these two pieces. So I could replace the 3x squared dx with simply a du. The remaining part, cosine of x cubed, would become cosine of u. And now I have a very simple antiderivative, which we know is sine of u plus c. And then I merely need to resubstitute u equals x cubed to get my final answer, just as we had before. Let's look at another example. Suppose I have the integral of 5x times x squared plus 4 raised to the 20th power dx. Now, I could actually work this out without our new substitution method. I could expand out x squared plus 4 to the 20th power and get a very long polynomial that I could integrate term by term. But that's not terribly practical, so let's see if there's a better way. What we did before was to let our u be the inside part of our integrand. Here the likely choice seems to be x squared plus 4. So going directly to differential notation, I can say that du equals 2x dx. Now I want a 5x dx, not a 2x dx, so I could multiply both sides of this equality by 5 halves. Now I have my 5x dx that I want. So this integral becomes, with this substitution, the 5x dx becomes 5 halves du, and here I have u to the 20th power. If I want, I can bring the 5 halves outside of the integral, and I know an antiderivative for u to the 20th power. This is going to be 5 halves times u to the 21st power divided by 21 and then plus some constant. So we have 5 over 42 u to the 21st power plus c, but u was x squared plus 4. And we raise that to the 21st power, add on the plus c, and we have our answer. If we're not sure we did this correctly, we could check our answer. We could take the derivative of 5 over 42, x squared plus 4 all to the 21st power plus some constant c if we want, and we get 5 over 42 times 21, x squared plus 4 to the 20th power, times the derivative of the inside part using the chain rule, 2x, the derivative of the constant is 0, and when I multiply 2 times 21, I get 42, so that will cancel with the 42, and I get 5x times the quantity x squared plus 4 raised to the 20th power, just as we desired. Now, sometimes we might want to use this substitution technique to work out a definite integral. Let's see a few ways of doing that. If I wanted to find the integral from, say, 0 to 1 of 5x times x squared plus 4 to the 20th power dx, I could use my previous result. Or if I hadn't already done all this stuff, I could go ahead and work out the corresponding indefinite integral, get this answer. All I need is some particular antiderivative, so I'll just let my constant be 0 now. And I evaluate this from 0 to 1. And when I plug in 1, I get 1 squared plus 4 is 5, 5 to the 21st power, so I guess I'll have 5 to the 22nd power, rather large number, divided by 42, minus, then when I plug in x equals 0, I get 4 to the 21st power times 5, divided by 42, and that's going to be my answer. This is usually the safest way to work out a definite integral when you need to substitute. Work out the corresponding indefinite integral first, and then just use that antiderivative that you get with the fundamental theorem of calculus. We could have done this a different way, though. If we were doing this from scratch, we might say, well, we want u equals x squared plus 4, the inside part of this 20th power function. So since I have this written down already, I'll use this substitution up here. And just as before, we'll get 5 halves du for the 5x dx, and this part becomes u to the 20th power. But this is a definite integral. This equals a number, and so I have to have a definite integral, a number, over here as well. But this is a u integral, so it must have u limits. We didn't write this over here, but we could have written x equals 0 to x equals 1. What would the u limits be here? Well, when x equals 0, u equals 4. When x equals 1, u equals 5. So we have 5 halves times the integral from 4 to 5 of u to the 20th du. We then find an antiderivative, u to the 21st divided by 21. We evaluate that between u equals 4 and u equals 5. And so we get 5 halves times 5 to the 21st power over 21 minus 4 to the 21st power over 21. And this is equivalent to our previous answer. Let's conclude by looking at a couple more anti-differentiation formulas, ones that aren't strictly substitutions, but that we'll find very useful as we move along. If I want to integrate sine squared theta d theta, I know what the antiderivative of sine is, but this sine squared causes something of a problem. I might ask myself, is there some trigonometric identity that would allow me to rewrite sine squared? Well, if we look at a list of trig identities, we might come across our identities for cosine of 2 theta. One of those is 1 minus 2 sine squared theta. Another version of this, which I'll write down here for reference, is 2 cosine squared theta minus 1. These are equivalent because of the Pythagorean identity, but we want to use this first one because if I solve this for sine squared theta, I now get something that doesn't have a trig function squared. It's just a regular cosine. So I could use this identity to replace sine squared theta in this integral. And now we just have to integrate this function, which should be somewhat less challenging. If I want to find an antiderivative for 1/2, and my variable is theta, I would guess that would be 1/2 theta. Here I have cosine. An antiderivative of cosine is sine, but I have a 2 in here, and I might, after thinking about it for a moment, guess that this should be 1/4 sine of 2 theta, and then plus some constant. If you don't see why this should be 1/4, we could use a u substitution with u equal 2 theta on this part of the integral. Now this other version of the cosine double angle identity can also be useful to us. We could write cosine of 2 theta plus 1 equals 2 cosine squared theta, and then dividing by 2, we get cosine squared theta equals 1/2 plus 1/2 cosine of 2 theta. So if we want to integrate cosine squared of theta d theta, we merely replace cosine squared with this equivalent expression. That's going to look very much like our last indefinite integral, except there's a plus sign here. So we should get 1/2 theta plus 1/4 sine 2 theta plus c. We can check both of these answers and differentiate them and make sure we get back sine squared theta and cosine squared theta respectively. I would not suggest memorizing the results of these integrations. Instead, I would remember these two formulas right here because they'll come in handy all throughout this course, and they're very similar, and so if you can remember where the minus sign goes and the plus sign goes, it's almost like remembering one formula instead of two.